The typical factory contains a complex maze of cables using a multitude of different communication standards, each with its own cable and connector type. You might find CAN, RS-485, RS-232, HART, FlexRay, LIN, Modbus, Profinet, and many, many more, each cable often routing to a single device. The cost to install, maintain, and debug these systems can be very high. With more things getting connected as part of the Industry 4.0 revolution, this problem isn't getting easier. Thankfully, new and improved solutions are here, so stick around and get a glimpse of a better future. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world. Today on Tech Chat, we welcome Arndt Schubel from onsemi. Arndt has an extensive background as a design engineer and system architect, and is now in technical marketing covering applications for Industry 4.0 and wired connectivity. Welcome to Tech Chat, Arndt.
Thank you for having me.
Yeah, good to have you here. Why don't you start us off by providing some context for our discussion today?
We'll be talking about, how the Industry 4.0 and is changing the way manufacturing will work in the near future. And alongside with that, we're going to introduce you to our recent device that we have put together for our customers, which is a 10BASE-T1S multi-drop device. So we'll have some content to cover about that later. The term Industry 4.0 is derived from the major revolution in industrial history. In this development, Industry 4.0 is considered the fourth major technological revolution. The timeline begins at the end of the 18th century with the discovery of water and steam power, also known as the first industrial revolution. This is followed at the beginning of the 20th century by assembly line and mass production that we refer to as the second industrial revolution. And in the 1970s, by the digital age, the third industrial revolution. Industry 4.0 describes the fourth major transformation for the industrial sector. Digitalization makes it possible a cross-industry and cross-technology integration of processes and systems that link everything together: production, services, logistics, human resources, and resource planning. The virtual world and the real world actually start to interact. This communication is characterized by many interfaces. Not only does that set new standards, it also needs new standards. And that is where Ethernet comes into the game.
That's a great reminder that our world is actually accelerating in the fact that each industry revolution that you've shown here kind of got closer to the one previous, and the timelines are getting shorter and everything just grows exponentially.
True. If we look on how that transformation will happen, we could look at, at what a current factory will work like compared to what that transformation into the Industry 4.0 age basically will transform that into. So this, I've shown this pyramid here where basically you see a typical factory as it looks today. A highly automated factory, all starting from the enterprise resource or the resource planning down to where the actual operators sit for the, it's called the MES, the manufacturing execution system, or the supervisory control and the data acquisition. And then it goes all down to, basically to the manufacturing floor with distributed control systems that can drive everything like servo drives and other actuators and sensors, to programmable logic controllers that check if doors are closed, or a part is loaded into a certain machine, or operators have their hands off in case there's operators. In this pyramid, everything that you see down to the yellow pyramid, so basically to the distributed control systems and the PLCs today, is dominated by Ethernet. This is what we today call the classical industrial Ethernet. This is systems working on 100BASE-TX. So that's basically the same that you plug into your computer today, 100 megabits, and there's a strong move towards faster speed with 1000BASE-T, which is a gigabit Ethernet, or even faster. As you create more data, you have more demand for faster data up in these levels. But down at the, which is today is called, the field I/O devices, pretty much you have proprietary or legacy bus systems that connect your actuators and sensors to the actual, distributed control systems or the programmable logic controllers. As you go down the pyramid, you also see that the number of wired connectivity down towards the field devices becomes more and more. So there's more wiring involved, and there's a strong move to move some of the intelligence as we do the transformation from a pyramid into what's called a column, where the field I/O devices take over some of the functions of the PLCs and the I/O modules, or the DSCs, the distributed control units. So some of that function merges into the sensors and actuators, making them smarter. As well, some of the functions of the PLCs move up to a factory on-premises cloud, where instead of having actual, PLC controller boxes that are built in hardware, now you can do them as virtual PLCs running on several servers. Alongside, there is machine learning, which helps you to react to situations inside your factory more flexible. Basically, what it comes down to is that factory is steering how the product is built. The advancement of the product as it runs through the factory tells the factory how it should react. That's the basic idea. And alongside of that, there's a strong call for making available data from the field I/O devices to not only to the on-premises cloud, but also uplink this into the global cloud for logistics purposes or maintenance, where companies providing the raw material could basically see the demand as your production flows through. Also, this would help you to sort out issues with actuators or sensors needing service, because with predictive maintenance and these sensors and actuators being able to be seen globally, a service provider could offer services to replace a sensor before it actually breaks and brings the entire factory to a full stop. As you can see down in the field I/O device level, as there's a lot of wiring, and most of the time you just want to retrofit your factory with a more modern view of how manufacturing is going to be done. There's a strong call for reusing wires that are installed in these factories already, and that's where basically the call for single pair Ethernet comes into the game. Today, this is 802.3 CG, the multi-drop short range standard. There is a second one which is called 10BASE-T1L for longer range, primarily used for process automation. And there's work going on to even enhance this for more stations on a multi-drop network or longer point-to-point enhancements. Those are being worked on today. The standards haven't been ratified.
Thanks for that overview of the modern factory layout, basically, and connectivity. Is the technology going to be really focusing on today? Is that at the blue level for the field devices?
Yeah, that's pretty much what it's going to. And, the IEEE has basically seen that for most of these I/O devices, the demand and bandwidth isn't overly high. So the ease of wiring is what's driving this. So let's have a look at what the IEEE 802.3 CG actually looks like. The standard got approved in late 2019, pretty much end of the year in Q4, and it was targeting industrial, automotive, and building technology systems, providing 10 megabits per second networking. There were 2 5 physical layer standards defined. One as being the 10BASE-T1L long reach for covering around about 1,000 meters. It's a full duplex point-to-point. We as a company took care of the 10BASE-T1S short reach or short range, 15-meter point-to-point and 25 meters multi-drop, where actually the point-to-point defined there is an optional full duplex, which we did choose not to implement, but we looked at the half duplex multi-drop because we quickly saw that this is where the cost savings in installations will come from. With traditional CSMA CD or plain Ethernet, in high loading situations, you're going to run into problems with reduced bandwidth and higher access time to the media. So IEEE called this physical layer collision avoidance, which enhances the multi-drop performance in situations where you have a high network load. And if you set that up correctly, collisions will entirely be avoided, and by using a round-robin arbitration approach, which allows every station to take its turn on accessing the media. The beauty of Ethernet here is that even if you change the physical layer, you can reuse everything else that you have. So your protocol stacks can remain the same. Everything above the MAC layer, actually the MAC layer itself can also remain the same. As soon as you connect a new PHY to a MAC, that's all you have to do pretty much, because the rest is predefined. Ethernet frames have a predefined format, so there's not much that you have to do by going down that road for 10 megabit half duplex Ethernet.
So this standard was approved about 2.5 years ago. Are you just now seeing the industry start to adopt because you guys are releasing the products that support it?
We're the first to show a MAC PHY device, which is a combination of a MAC and a PHY, which is a perfect device for building small size sensors, because you can hook this to a very, very simple microcontroller that wouldn't even know about Ethernet. We have some examples to show later that basically, when we show you the device itself, you'll basically see how this goes together. To see the beauty of this physical collision avoidance, for physical layer collision avoidance, I think first you have to understand how the classical CSMA CD, which stands for Carrier Sense Multiple Access with Collision Detection, to find out how that really works. And assume these stations are 0, 1, 2, 3 from the left. And I'll think of station 0 wants to send data. So it puts its data on the line and it sends it along. For this particular example, it wants to send to station number 3. All the others, because this is a bus system, they can listen. They see the line busy, so they don't do anything. The receiving station picks up the data. Everything's fine. So no problem here. But if all see the line as free and 2 will try to send data at the same time because they have data to send, then eventually the data, creates a collision. The receiving, the passive stations, like the one receiving and the one you just doing nothing, they just see the line being busy. They don't know what's happening. But the other two monitor their own traffic, and as the traffic coming back due to the collision is not the same that they send out, they say, hey, it's a collision. My data didn't make it through. It's corrupted at the other end, so I have to do something against it. This is where CSMA CD comes in. So this is a carrier detection or collision detection, while the line busy from the other one is basically the multiple access carrier sense. So what they do in this particular situation, the two stations that want to send their data, they wait for a random amount of time. And it's important that they wait for a random amount of time because eventually one of the two wins. So if we look forward to what happens in this particular situation, station number 1, so the second from the left, probes the line. It does a carrier sense. So basically it looks for energy on the line, and if it doesn't find anything, it says, okay, the line is free. It's not occupied. I can send my data, while the other station, the one to the left, is still in that waiting mode, waiting for random time. So next thing that happens is that station will send its data. The others see the line busy, there's receiving, and the station that would still have data to send, the one to the left, it senses the media again after its random time and says, oh, the line is busy, I still have to wait. So it waits a little longer and just waits for the packet to go through. And eventually, it probes again while the second station to the left is done. It sends its packet. The other one, all of a sudden figures out, oh, the line is free. Nobody's sending. It's my turn. I still have data to send. And that's when it puts the data on the line and sends it to the receiver.
All right. Well, that was very helpful. Why don't you explain to us a better way to do this? So
a better way, that is what the IEEE came up with, physical layer collision avoidance. Let's see how that works. So in PLCA, physical layer collision avoidance, it all happens on the physical layer. The upper layers, like the MAC, the media access controller, and everything above this, which is typically built in software from layer 3 onwards, they don't know about this. What you have to do is you have to assign every station a single ID, an identifier. In this particular case here, from the left to the right, we call them 0, 1, 2, and 3. And the station with the ID 0 gets a special role. We call that the coordinator. And what that does, it sends a beacon. It's a 20-bit long signal that denotes the start of a PLCA cycle. So this one, like here, sends a beacon, and that beacon travels along the line. Everyone sees that, and they reset what's the transmit opportunity counter. Let's see how what's happening next. If all of them have a counter of 0 by having seen the beacon, and now the idea is if your counter matches your ID, that's when you can send data. So in this particular example, here you see that station to the left, the coordinator. It reset all the counters, including itself, and it sees the counter being 0. So it says, oh, the transmit opportunity counter is at 0. So that's my turn to send because my ID is 0 as well. So it takes control of the data line and it sends its data to wherever it wants to send it to, right? All the others don't do anything unless they have seen the data packet passed. They increase their counter. Now, with the counter being 1, the station with the ID 1, with the PLCA ID 1, here in this particular example, the second to the left, says, oh, the counter is 1 now, so it's my turn to send. So it can take its data, while all the others say, wow, when the counter doesn't match my number, I'm not allowed to send, so they remain silent. So this basically guarantees that station number 1 has sole access to the media and can send its data without creating a collision. So it sends its data to whomever wants it. And it continues. Counter goes to 2 after the data packet is sent. So the station with ID number 2 knows it's its turn. It sends its data. The counter increases again. It goes to 3. Number 3 knows it can send data. It sends its data. And then at the end, the counter goes to 4, but there is no 4. But what actually happens is the coordinator, ID 0, the one to the left here, has been told by configuration that there's a total of 4 stations in this particular example, which is basically only used to demonstrate or illustrate how this works. So it sees counter number 4 and it says, okay, the maximum ID that I have been told you should see on your counter is 4. So when it sees that, it restarts the cycle because it says, well, there's no number 4 here. I've been told the cycle ends at number 4. Let's send a new beacon. All the other stations reset their counters, and the cycle starts over.
So is there kind of mechanisms for, let's say, if site number 1 doesn't have data? So does it basically send a no op on the line so that it passes that, increments the counter, I guess, and so the next one can go?
Yeah, there is. Every station has a chance to pass on its transmit opportunity. Imagine that in this particular setup, station number 1 doesn't want to send, although it matches its counter, which is called the transmit opportunity. What it does is it responds with silence for a certain length, which is basically a timeout principle. So for the timeout is defined by the IEEE to be 32 bits times. So if a station doesn't respond to its transmit opportunity within 32 bit times, all the stations increase their counter by saying, okay, this station had the opportunity, but it wasn't using it, so let's increase or increment.
Oh, that makes actually more sense because then if the one station goes offline or is broken or something, the whole system doesn't come down waiting for that no-op, as I was theorizing.
Absolutely. It's a timeout mechanism that works here. So let's have a look what that means if you increase your data throughput. So here's a simulation of, of a PLCA system versus a non-PLC CSMA CD system with 8 nodes and the minimum size Ethernet frames, which is 64 bytes of payload. To the left, you see the number of transmitting nodes versus the throughput, and you could see as you get more transmitting nodes coming from one. Well, one doesn't make sense because if you have one node, it can't send data anyway. But you can also see if you have 2 nodes talking, half duplex point-to-point installation, your throughput drops to round about 8.5 megabits per second, while in PLCA, due to this round-robin arbitration where everyone gets to send one after the other, you can utilize the network to the extreme. You can be very close to 10 megabits. While if you increase to up to 8 stations for this particular example, your effective throughput on a CSMA CD system, and keep in mind, this is just a simulation of one situation. If you go longer frames, the situation is getting worse. But for minimum size frames, you drop down to 6 megabits per second. If you go more stations, it becomes even worse. So figure if you had 40 stations on a net and all of these stations will have to send, you're dropping down to an extremely low number. Another thing that becomes apparent is the time you have to wait until you can actually access the media. We call this the access latency. So if you want to send a packet, how long on average or maximum do you have to wait till you own the media? So in PLCA, this is fairly constant. It's everything between 64 best case and 440 roundabout. While in CSMA CD, you have a huge difference. Like if you look at 70% bus load, and by the way, the higher the bus load, the worse your access latency becomes on the CSMA CD system. So for like 70 to 80% of a bus load, you can see everything between a millisecond and almost 60 milliseconds, while the difference on PLCA is just, a couple of microseconds. So that's basically another indicator for how effective PLCA takes use of the available bandwidth.
Yeah, and it's important to note on that access latency graph you got there, that's a log scale. So it's 100x improvement.
Roundabout, yes.
Yeah.
So this is a view of, why does it make sense? What are you trying to achieve with this? So as we said on one of the very early slides, we kind of said, there's more call for data that can be seen everywhere. So with the existing protocols like the hard modems or the RS-232, the normal serial protocols, CAN, FlexRay, you name them, you always need gateways that translate from one world to the other. But what if your entire factory installation would be Ethernet? Then you can make that data available to everyone at no matter what level, even probe a sensor from the internet or from the cloud. So you could send more data alongside low. So a temperature sensor would be able to not only tell you, the temperature, it could tell you how much current it consumes. And from that, you could probably guess if it's healthy or not. You could check it against, the temperature of temperature sensors in close proximity to see if they all agree with the temperature measurement. Stuff like that. And, you can do this outside of the actual control loops by, using higher level or higher layer instances that only look at the health of your sensor or of your actuator and stuff like that. So that's the real motivation that the IEEE came up with to say, okay, this entirely makes sense. Let's go Ethernet all the way. That's, I think, what they called it. Here's a little more of a illustration of what the round-robin PLCA will look like. Here you see the minimum bus cycle with no station sending, and you have a maximum bus cycle where all the stations on your network will try to send data, or they have data to send. Okay, so where does that make sense? We know for a fact, it's a short-range system, so it's defined to go 25 meters. We can actually do a little more. We have it running in the lab to around about 50 meters. If you think of cabinets, in-cabinet wiring, like we show on this picture here, where you can have motor starters, contactors, relays, whatever. On a typical cabinet, on the front door, you have gauges, you have push buttons, so-called pilot devices. And if you look at this particular picture, you see the amount of wiring that goes into a cabinet like this. And now this is also called the marshalling cabinet that basically makes a connection between all of these devices inside the cabinet. Now think of the installation process itself. A trained technician would roundabout take 6 minutes to pull one of these wires. Like figure the situation where you have to repair this cabinet. So you basically have to, you have to check your schematic, you have to find the right wire, you have to see how it's run through the cabinet, you eventually have to pull it if it's broken, or at least you have to replace, your contactor or pilot device or anything like this. So it's an error-prone process, and it takes long, especially for the installation. But what if you can take these wires and replace them by a single, Ethernet bus and run that across your cabinet? So what we have shown is we can run 40 nodes in a situation like this on a 20-meter single pair cable. The standard says 8 on 25, but we have proven in the lab that we can do 40 nodes on 25 meter segments. Also, we've tried with a lower number of devices, and we can reach distances in excess of 50 meters.
So in these new systems, if we look at the diagram at the lower right, the new and improved system, which points will utilize your onsemi T1S PHY? Is it, I mean, it's obviously the field instruments, but is it also moving up? Is it the junction boxes?
You can have that in the junction box. So the nice thing with our MAC-PHY device, it can be used on low cost microcontrollers, or it can be used on complex SoCs. All it has to have is a SPI interface that runs 15 megahertz. The rest is more or less done in software. The fact that the MAC is integrated is you basically send it full Ethernet frames, and the MAC-PHY takes care of the rest. So where you see the yellow Ethernet cable in between the cabinet system and the marshalling cabinet, you'd have a PHY or a MAC-PHY at each of these ends, and obviously to your field instruments as well. So both of that makes sense. If you have a lot of field instruments and you want to concentrate, then you could think of using that yellow wire to be like a link aggregated faster Ethernet link, like for instance 10BASE-TX.
And that's very interesting. It's one of the real elegant solutions here is the fact that you don't have to change anything at the MAC and above, because it allows an operator to kind of do a rolling change out of a system, because everything's going to be Ethernet at that high level anyway.
Absolutely. So if you, like in this particular situation, if you have a push button on the front door and you want to change its function, you don't have to rewire anything. You don't have to reposition the buttons. You just reconfigure them. And then they send messages and they go through that unified network architecture. So they're always Ethernet frames, whatever payload they cover. All you have to do is basically react to that payload and assign it a function in your controllers, I/O controllers, or you name it.
Right. That's an easy switch. No pun intended, since it might be a switch.
It might be a switch.
All right. Well, what else do you have for us today, Arndt?
Yeah, let's have a look at the actual device. So the device we had actually put on the market earlier last month we call it the NCN26010 device. It's a 10BASE-T1S industrial Ethernet controller. If you look at that basic block diagram, what you see inside the device, beside from the power conditioning, so there's it runs off a single 3.3 volt, but it has some regulators inside to get you all the voltages we need internally. It has a PHY and a MAC combined, and the interface to a host is actually an SPI interface. So you only have 4 pins. You have an SPI clock, you have a chip select, you have a master in slave out, and you have a master out slave in. We're running a predefined protocol defined by the Open Alliance. That's coming from in-vehicle networking, but they've put some effort in providing a specification for SPI protocol that does the trick here. So we basically adopted that, and we realized that 10BASE-T1S will have a second life in automotive, so it makes a lot of sense to take on that protocol. We have physical layer collision avoidance. We've shown you how that works in principle, so that's on board. And we have a feature that we call enhanced noise immunity. And what that does, it doesn't really only look at the signal levels on your cable. It also takes use of the system or the signal's properties, and it's using some DSP functionality to extract that signal from noise, which helps us to extend the range. Like I said, we can cover 50 plus meters. It also helps us to extend the number of stations on a net. I said earlier we have tried 40. And that basically, extending the range and, extending the number of stations helps you, again, cutting down costs, because figure if instead of 8, you can now put 32 stations on a 25-meter cable. You wouldn't need 4 segments. You only need 1 segment. So that saves you a switch port at the other end. So that's basically where another saving comes in. More stations on the same cable gives you a higher cost saving. You could use that MAC-PHY together with a low-cost microcontroller and turn this into a sensor node.
Well, that sounds excellent. For developers interested in getting started now with implementing products that use this technology, what resources do you have at onsemi to help them get going?
We do have an eval board or eval kit. So basically here you see a picture of the eval board. And it contains, for an easy start, we have this connect to a Raspberry Pi. For best results, if you connect it to Raspberry Pi 3 as a host, you can use the system and turn the Raspberry Pi into a fully enabled 10BASE-T1S node. So the block diagram down in the lower corner shows you how that works. You have the Raspberry Pi. It connects to what we call the bridge board. That's on the picture. It's the board to the left. All it does, it basically takes that standard PMOD connector that the EVB, the eval board, has, and translate it into the right signal positions on the 40-pin Raspberry Pi connector. And also it acts as a power source. You can feed it anything between 8 and 28 volts, and it regulates it down to 5 volts for the Raspberry Pi, and it also generates the 3.3 volt to run the NCN26010 eval board. So these boards can be ordered single or as a kit. The actual eval board is the NCN26010 XMN-EVB. You can order this standalone if you want to hook this to a normal, microcontroller rather than a Raspberry Pi. That's all you need. It has these two RJ45 connectors. For an easy start, you can plug in any Ethernet cable you find as long as it's not crossed. But it's only using one pair inside that cable. So you can crimp your own cables or just use a normal Ethernet Cat5 or Cat5e cable to get started. And then if you want to, or if you intend to connect to a Raspberry Pi, that's when you need what we call the bridge board, NCN26010 BMN-EVB. So that the B stands for the bridge board. That's the actual signal adapter plus the power supply on one board. Or if you know that you need both, you can also order this as a kit. So this is what, this pinkish color says, if you order the NCN26010 XMN-EVK, you basically get both boards. And that enables you to put a Raspberry Pi on it. But as soon as you hook this to a Raspberry Pi, you basically have an enabled node.
Well, Art, that was an excellent detailed introduction to some exciting new technology that I think is going to be very beneficial to people working particularly in the control automation space.
Well, it is. And, like we show in the cabinet example, we're not limiting customers to basically use this only in cabinet applications. We think there's way more that we haven't even thought of. And as we see people using this technology, we would like to learn from our customer base or those of Mouser to understand, what people could use that for. So, the more people they use it, we are convinced they come up with more ideas on how it can be used.
I suspect you're exactly right. Now, if you're interested in any of the onsemi products we've discussed today, head on over to Mouser Electronics, our sponsor for today's Tech Chat. And as Arndt mentioned, if you have some ideas and want to talk to them, reach out to onsemi. There's the contact information there. And please join us again next time on Tech Chat, where we chat with the leading technical experts like Art Schubel from industry-leading companies like onsemi, who are changing our world every day.